Hello everyone. In today's class, we will see how we can implement linear regression. As you can see on your screen, I have opened the Google Colab platform, and here we will try to implement linear regression algorithm. First, let me import the NumPy library, which is essential for this. I have taken the same example that we discussed in the last class. If you remember, x values contains these values -2, 1 and 3, and the y values were -1, 1 and 2. We have defined that as an NumPy array, and we have also reshaped them. Why? Because many NumPy operations are done only on two-dimensional array. Here we define them only as one-dimensional, so they need to be converted into two-dimensional. We do that with the help of reshape function. Let's run it also. If you remember the compact matrix form of linear regression, in that we need to add a column of ones before x. We can do that very easily with the help of inbuilt NumPy functions hstack and ones. The NumPy ones function will create a column of y because we have given the dimension 1 here, and we will add that before x. So when we will run this, you will see that we have added a column of ones before the actual x values, that is -2, 1 and 3. Let's move forward and try to calculate the major expression. It is available in the linear algebra library of NumPy. We will try to calculate the inverse of x transpose x. Here the dot operation tells you the matrix wise multiplication. Once we have calculated the inverse, then we will multiply it further with the x transpose, and finally we will multiply that with the y value. When we will run this, it will calculate the coefficients of the linear regression line. Further, we can print this and we will get approximately the same values as we saw in our lecture in the previous class. Finally, once we have identified the coefficients of the linear regression line, we can test it on a test sample. For that, I have taken the value 4 but added 1 here because in the compact form you have to add the column of ones before the actual value. Here also we are reshaping it to make it compatible for the matrix operations. Let's run this further. And when we will multiply this test sample with the vector of coefficients, it should give us the value of y, corresponding y. It is a prediction value, and the value we are getting here is 2.68. It means that for the value of x being 4, the corresponding estimated value of y is 2.68421053. Rather than identifying the value of x test value with matrix operation, we can also directly calculate that. It is, let's define x test as 4, and our a vector contains two coefficients. We can identify them with a0 and a1, and when we do that and multiply that with x test, we get the same value as we got earlier as the predicted value of y. So as you can see, it is very easy to implement the matrix form in Python. However, there lies the direct implementation also. There are libraries available in the Python like sklearn, where the direct implementation of linear regression is available. Let's try to implement that with the help of inbuilt libraries. The first step is that we need to import the necessary libraries. In this case, we are importing NumPy and sklearn linear model, we have to prepare our data with independent variable x, independent variable y. We have taken the same values as we have taken earlier. We will first create a model, linear regression model in this case, and then we will fit the model, which is linear regression, on our given data set x and y. Here we need to once again reshape x but not y. When we will run this, then our data is trained on the available training data set. The next step is to test the performance on a testing set. For that, we have once again taken the same value, x test is 4, but we have defined that as a NumPy array. When we run this, then this test sample is created, and to predict the value of y for the given value of x test, we simply use the model's method predict. This method will take x test as input and then will give us the corresponding value of y. Let's see that. After completion, we will print the y value, and as you can see that we got the exact same value. So either we can implement the linear regression using matrix form by itself, or we can also use the inbuilt libraries for the same. Sometimes, however, we do not want to fit a simple regression line, but rather want to fit a polynomial equation. Let's see how we can do that. In this case, we have added one more functionality of sklearn library called polynomial features. This part helps us to create higher order polynomials of our independent variable x. So let's first import the library. We have the exact same data set. Now using this code, we can create the higher order polynomials of the independent variable x. In this case, the degree is 2, means the higher order is only 2. By passing the degree into polynomial features, we will calculate polynomial features, and on the basis of polynomial features, we will supply our data x to it. When we do that, then we get the polynomial features of x. Let's try to print that. So when we print the polynomial features x poly, you will see that the middle column is the actual x value. On this side, we have got the ones as columns, and on the right side, we have got the squared terms, which is x square. So polynomial features is a very convenient way to calculate much higher order polynomials of the independent variables. The rest of the process will remain same. We will first create a linear regression model, but this time we will pass a polynomial feature to it. Now our model is available for prediction. We can test that on our test data. In this case, x test is 4. However, since our original model now works only on polynomial features, we have to first convert our x test also into the corresponding polynomial features, and then only we can do the predictions using the predict function. Let's see that. Finally, we can display the results, and the answer is 2.4. So as you can see that when we try to fit a simple line using linear regression, the output for the same value was 2.68, but when we try to fit a polynomial to that, the answer, the predicted value, now has become 2.4. So depending upon the application, either we can go for the line, the linear combination, or we can also try to explore the polynomial features. Now let's try to take a real world application for the same. of house prediction. In the case of house prediction, we have many independent variables, and on the basis of that, we want to predict what would be the price of a specific house. Let's see the data and let's see how we can implement the same using linear regression. First of all, the data is available in my Google Drive, so I will upload my drive. So my drive is mounted successfully. The next part is I have to import necessary libraries. So Panda library is there to read the data, NumPy library is there, sklearn library is there, and within sklearn also we have train and test split functionality, we have label encoder functionality, we have linear regression functionality of course, and finally we have to calculate some performance measures also. In this specific case, I am considering two measures, mean squared error and R squared values. Later on, we will discuss what do we mean by these performance measure and how we can make sense of them. Let's try to import these libraries first. So the libraries have been imported successfully. The next part is to upload the data. For that, I have given the specific path of the data which is available in my drive, and using pandas PD, we will fetch the data from the drive and store that into data variable. Furthermore, we will try to see a few lines of the loaded data. As you can see here, there are many independent variables like longitude, latitude, median age, total number of rooms, total number of bedrooms, population, households, median income, ocean proximity, and finally, what is the price of this house in median terms. Let's also see how much data is there in the file. So overall, there are 10 columns. Out of them, 9 are independent variables and the last one is dependent variable. And there are a total of 20,640 rows in this data set. Though the data set seems fine, but there is one problem. That is, the ocean proximity column contains non-numeric values. Let's see them. So ocean proximity has these 5 values: less than 1 hour from the ocean, inland, near ocean, near bay, and island. For linear regression to work, all the available data should be numeric. So we have to somehow convert the values of ocean proximity, which are these 5 values, into numbers. There are many ways in which we can do that. One very common way is to convert the corresponding category into some number, and we can achieve that with the help of label encoder functionality. What this encoder does is it takes the nominal data which is in the form of a string and converts that into numeric data. How does it do that? For all the 5 values which are available in the ocean proximity column, some value might be assigned a number 1, some value might be assigned a number 2, and so on. So for example, in this case, when we run this whole code, the near bay value has been assigned a number 3. The benefit of this now is that the available data now is in the form of a number, and linear regression algorithm can be applied easily on that. Just remember that after conversion, we have added a new column into our data called ocean proximity encoded, which contains the encoded values of this column. Once again, since we have done the encoding, we do not need the ocean proximity column anymore. So we are deleting this column from our existing data. Also, the data contains some blank values also. NA here stands for not available. So we are replacing those values with the median values of the column. Let's try to do this operation also. So when we do that, as you can see, that ocean proximity column has been removed, and in place of that we have this new column ocean proximity encoded, which has the encoding of the corresponding categorical values, and the missing values have also been replaced with the median values of that specific column. Since the available data contains both the independent variables and dependent variable, from X we have to delete the median house value, something that we want to predict, and the median house value should go in the Y variable, the actual values. So this is the code to achieve the same. Once we do that, next is we try to divide the available data into our training set as well as the test set. For that, we use the inbuilt functionality, which is train test split function. It takes the X values, it takes the corresponding Y values, and it takes what should be the size of the test data. And usually we also supply a random state value, which could be any value. The benefit of this value is that later on, if you want to reproduce the result or want to do the same split, you need to use the exact same random state number. Let's try to do the splitting. After splitting, let's try to check what is the size of training data set and testing data set. So the overall data set has been divided like this. It contains the 10% of it, and the rest of the 90% is my training data set. You can also check now the number of columns in X are 9, which means it contains 9 independent variables. Now rest of the process is same. We will create a linear regression model and we will fit it using the training data set X-train and Y-train. Once we have done that, the next part is let's do the predictions on the training data set. How good my model is performing in predicting the right values of Y for the same training data set from which it has learned. Let's try to run this further. So we have made the predictions for the training data set. Let's try to check what is the difference between the actual training values of Y and the predicted values of Y for the training data set. For that, we use the inbuilt functionality of mean squared error. It tells us the amount of difference between the actual values and the predicted values. We have also scored a very famous performance measure, we call it R-score. Its value lies between 0 and 1. The more it is closer to 1, the better the prediction is. We will discuss the R-squared error later in the new or upcoming lectures. So when we do that, you can see that mean squared error is this much for the training data set and the R-square value is this much on training data set. Now comes the major task, which is what the performance of the model would be on the testing data set, which it has never seen before. For that, we are passing the testing data to it and we will make the predictions. Later on, we will check what is the amount of error for the testing predictions and actual test values, and we will also calculate the corresponding R-square score. So as you can see here on the testing data set, it should be testing data here. On the testing data set, the error is this much and the corresponding R-squared value is this much. So it is lower than the training data set, but is still in performance, it is closer to the training data set. So this is the way you can implement the linear regression algorithm using the inbuilt Python libraries for very complex but real life data sets. Thank you.